You believe objects have properties even when nobody looks and that nothing can influence something far away instantly. Good. Now take two particles, separate them light years apart, and let each of us choose how to measure. A simple counting rule says your common sense package can't survive. Imagine you and I agree on something that feels almost too obvious to say out loud. The world is made of things. A table is over there, a lamp is over here. They each have properties right now, whether or not anyone is staring at them. The lamp has a color, the table has a temperature, and what happens over there shouldn't instantly affect what happens over here unless something physically travels between them. That obvious package has two pieces. First, asterisk, realism, asterisk. The idea that a physical system carries its properties with it. Measurement is like opening a drawer. You discover what was already inside. Second, asterisk, locality, asterisk. The idea that influences don't jump across space faster than light. What you do here can't immediately rewrite what's true over there. If you grew up on classical physics, those two feel like the rules of sanity. Not because of philosophy, because of how you survive. You don't bet your life on a bridge if its strength is only decided when you look at it. You assume it either holds or it doesn't, and your looking doesn't create the steel. Now, here's the problem. In the quantum world, there are situations where you can't keep both pieces of that package. Not it's hard, not we don't know yet. I mean, you can write down a clean mathematical inequality, something any locally real theory must obey, and nature violates it. Let's build the pressure slowly, because this is where people usually get hypnotized by the word quantum and stop thinking. Start with a simple picture. Two sealed envelopes. Envelope A goes to you. Envelope B goes to me. They're separated across town, across the planet, across the solar system. Doesn't matter, they're sealed. We agree on a rule. Inside each envelope is a number, either 0 or 1, and we're not allowed to peek until later. Now ask the realist question, are the numbers inside the envelopes already determined? If you're a realist, you say yes. The paper inside the envelope has ink on it, whether or not you open it. Opening doesn't create the ink, it reveals it. Okay, now ask the local question. Can opening your envelope change what's written in mine? If you're local, you say no. There's no magical pen in my envelope that waits for your hands to touch your envelope and then scribbles. That would be influence with no messenger, faster than light. So far, we're just stating the rules your brain already uses. Here comes the twist that makes this a physics problem instead of a philosophy problem. We are allowed to choose asterisk. How asterisk we look. We're allowed to choose different kinds of questions to ask of the envelopes. We in the envelope story, that sounds weird. In the lab, it's natural. Because in real experiments, we're not opening envelopes. We're measuring things like polarization of photons or spin of electrons. And measuring spin doesn't mean one single question. It means you pick a direction, this axis or that axis, and the answer you get depends on which direction you chose. So upgrade the story. You and I each receive a particle from a source in the middle. The source emits pairs. One comes to you, one to me. They fly apart. We separate them so far that no signal traveling at light speed could go from my measurement to yours in time. And right before measuring, each of us chooses a setting, 2 or 3 possible settings. Think of it as rotating a filter to different angles. Each measurement gives a binary result. Call it +1 or -1, a click in detector A, a click in detector B. Simple. Now ask the locally real question in this upgraded scenario. If realism is true, then each particle should already know what it will answer for every setting we might choose. Maybe it carries a little instruction sheet. If you measure along setting 1, answer +1. If you measure along setting 2, answer -1. And similarly for my side. If locality is true, then my choice of setting can't reach over and rewrite your instruction sheet at the last instant. The particles separated. Whatever they are, they have to carry the relevant information with them, or else behave in a way that doesn't depend on distant choices. That's the heart of the Einstein-Podolsky-Rosen worry, the EPR argument. They looked at entangled pairs and said either quantum mechanics is incomplete or it's allowing spooky action at a distance, and they strongly preferred incomplete, because incomplete is fixable. Spooky action feels like giving up. Now you might think the whole debate is just semantics. Maybe measurement disturbs things. Maybe the device kicks the particle. Maybe it's all messy. That's the usual escape route. But Bell's inequality doesn't care about that escape route, because it doesn't assume perfect measurement, or gentle measurement, or any specific mechanism inside the device. It asks a more brutal question. If the answers are locally predetermined, if there really are values there before measurement, and no faster than light influence, then the correlations between your results and mine must obey a certain numerical limit. not a vibe, a limit, and nature breaks it. Let's say it in plain language. If both envelopes have pre-written answers for every possible way we might open them, then there are only so many patterns the answers can have. When you count those patterns carefully, you get an inequality, a ceiling. Quantum experiments punch through that ceiling. This is why the "it's just disturbance" line doesn't save you. Disturbance can change what you read when you open your envelope. Sure, but if the envelope's contents were fixed in advance for all the different opening methods, then no matter how you try to hide behind ignorance, the statistics can't exceed the Bell limit. Bell's inequality is a trap. You step into it by insisting on both locality and realism, and once you're in, the only way out is to deny at least one of them. Now here's the part that people misunderstand in a way that ruins the whole topic. Violating Bell's inequality does not mean you can use entanglement to send messages faster than light. You can't. The outcomes on each side still look random locally. You can't decide to get +1 or -1 at will, so you can't encode Morse code into the universe with it. No superluminal texting, no time travel hacks. What it does mean is subtler, and in a way worse for intuition. It means the idea that the universe is made of independent local pieces, each carrying its own private set of properties, cannot be the full story, because the correlations are too strong to be explained by local pre-written instructions, and too structured to be written off as mere coincidence. So you're left with a very uncomfortable menu of options. Option 1, keep realism, drop locality, allow some kind of non-local influence, something that ties distant outcomes together in a way that isn't mediated by signals traveling through space in the ordinary sense. Option 2, keep locality, drop realism, say the outcomes aren't fixed until the moment of measurement, not we didn't know, not hidden under the rug, literally not there as definite values in advance. Option 3, drop something else you didn't realize you were assuming, like measurement settings are freely chosen, or the world has one consistent history. People do explore these, but now you're playing with the foundations of what it even means to do an experiment. And if you're tempted to say, well, maybe the particles secretly communicate, notice what the experiments do. They separate the measurements so that any communication would have to travel faster than light. They randomize the measurement settings at the last moment. They close loopholes. They do it with photons, with electrons, with atoms. Over and over. Different labs, different countries, different decades. The universe keeps giving the same answer. You don't get to keep the classical story. So when we say the universe isn't locally real, we're not being poetic. We're making a precise claim. You cannot simultaneously hold that A, measurement outcomes were predetermined properties of each particle, and B, those properties are only influenced by things in their immediate past light cone. No instant distant connections. The lab says no. And now the real question becomes, if the universe is not locally real, then what is it? What replaces the picture of objects with properties? If it isn't a set of local facts stitched together, what is the stitching made of? In the next part, we'll corner the logic properly. We'll take the envelope idea and turn it into a set of choices and counts. Still no heavy math, just unavoidable reasoning, and you'll see exactly where local realism gets trapped and exactly how the experiments spring the trap. Good, let's build the trap. We'll keep the story as concrete as possible. 2 separated labs, 2 measurement choices per lab, and outcomes that are always just 2 possibilities. Call your side A, call my side B. On your side you can choose setting asterisk, asterisk A, asterisk, asterisk, or asterisk, asterisk A, asterisk, asterisk. On my side I can choose setting asterisk, asterisk B, asterisk, asterisk, or asterisk, asterisk B, asterisk, asterisk. Each run of the experiment goes like this. 1. A source emits a pair. 2. 1 particle goes to you, 1 to me. 3. At the last moment you choose A or A4. 4. At the last moment I choose B or B5. Each of us gets an outcome. +1 or -1. No fuzzy outcomes. No sort of. A click here or there. Now, what would local realism say about one single run? If realism is true, then before we measure, each particle carries definite answers for all possible settings, even the setting we didn't choose. That's the key move. It sounds innocent. It's the same thing you believe about the envelope. If I could have opened it from the left or from the right, the number inside doesn't depend on which side I open it from. So in a locally real model, a single pair has an instruction table like, on a side, outcome for A is either +1 or -1, and outcome for A is either +1 or -. On B side, outcome for B is either +1 or -1, and outcome for B rets is either +1 or -. And locality says my choice between B and B pret cannot reach across space and change your pre-written outcomes for A and A pret. The instruction table is set at emission, or set earlier, but it's set Now here's where Bell did something almost insulting in its simplicity. He didn't guess the instruction tables, he didn't try to build the hidden mechanism, he just said, fine, whatever the tables are, they must obey a certain bound when you average over many runs, because the only ingredients are +1 and finer 1 and basic arithmetic. Let's talk about correlations, because that's what experiments measure. For a given choice of settings, say A, B, we repeat the experiment many times and compute how often the outcomes match. If A and B tend to give the same sign together, the correlation is positive. If they tend to give opposite signs, the correlation is negative. A convenient number physicists use is the expectation value, EAB, which ranges from finer 1, always opposite, to +1, always same. Now Bell's version that's easiest to explain in words is the CHSH inequality. Don't panic, you don't need the formula, you need the logic. Consider this combination of 4 correlations: finer EAB, 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 finer. We're going to add 3 of them and subtract one of them in a particular way. Why that way? Because it forces the hidden instruction tables to show their hand. Define S equals sign EAB plus EAB plus EAB meaner EAB. Bell showed if local realism is true, then asterisk asterisk vertical bar S vertical bar Lehine 2 asterisk asterisk. That's the ceiling, that's the cage. And the amazing thing is this bound does not depend on what the hidden variables are or how complicated the unseen machinery is. It only depends on the assumption that each run has predetermined outcomes for AABB, and that choices on one side don't alter the predetermined outcomes on the other. So why is the bound 2? Here's the simplest way to feel it. Forget averages for a moment. Look at a single run with its single instruction table. In that run, the outcomes for each setting are already fixed numbers. AA is either +1 or Vena 1, AA is either +1 or Vena 1, BB is either +1 or Vena 1, BB is either +1 or Vena 1. Now build the single-run version of S. S equals sign AABB plus AABB plus AABB minor AABB minor. Notice each term is a product of 2 minor 1 numbers, so each term is itself minor 1. Here's the trick, factor it. S equals sign AABB plus BB plus AAB minor B minor. Now BB and BB are each minor 1, so what can the brackets be? Minor phi BB AA, then BB plus BB is either +2 or -2, and BB minor BB is 0. Minor phi BB AA, minor phi BB minor BB plus BB is 0, and BB minor BB is either +2 or -2. Either way, one bracket is -2 and the other bracket is 0, so S is either +2 or -2. It can't be 4, it can't be 0. Actually, it can be 0 in some variants, but for this structure it lands at -2. The important thing, asterisk asterisk, the magnitude can't exceed 2 asterisk asterisk for any single run. And if every single run has vertical bar S vertical bar Li AN2, then the average over many runs also has vertical bar S vertical bar Li AN2. That's it, that's the inequality. No mysticism, no quantum vocabulary needed. Now comes nature's reply. Quantum mechanics predicts that for certain entangled states like the single state of 2 spins or polarization entangled photons, you can choose settings angles such that the measured correlations produced vertical bar S vertical bar can be as large as 2 root 2.8, 28 asterisk, asterisk, not 2, not a little above 2 because of noise, 2.828 in the ideal case, and experiments get close, again and again. This is the point where a reasonable person should feel cornered, because the logic is clean. If the world were locally real in the envelope sense, then those 4 correlations can't collectively be that strong, they can't line up in that pattern. But in the lab they do. So where did the locally real reasoning sneak in, an assumption you didn't notice? It's this sentence. The outcomes for the settings you didn't choose still exist as definite values. That is realism in its sharpest form, counterfactual definiteness, the belief that unperformed measurements have definite outcomes waiting in the wings. Classical physics loves that sentence. Your intuition loves it, your language is built around it, but Bell tests force you to pay for it, because if those unchosen outcomes are real, they constrain the chosen outcomes in a way nature refuses to obey. Now at this point people often grab the most dramatic interpretation, so measuring here instantly changes reality there, and I want to slow you down. because that phrasing smuggles in a picture of little objects carrying little properties that get rewritten by a distant event. That picture may be exactly what's failing. What the experiment's force is not necessarily a literal signal traveling faster than light. Remember, you can't use this to communicate. Your local outcomes still look random. No controllable knob, no message. What the experiment's force is something more abstract and more unsettling. The joint reality of the pair is not equal to reality over here plus reality over there, stitched together locally. The correlations behave as if the pair is one system even when separated, in a way that cannot be reproduced by local pre-written answers. So the envelope analogy is useful, but it breaks in a specific place. A real envelope can contain a pre-written number independent of how you open it. A quantum system can be in a state where the outcomes are well-defined only relative to a measurement choice, and the joint statistics are not decomposable into two separate sets of local hidden facts. That's why people say not locally real. Locality says no faster-than-light causal influence. Realism says properties exist prior to measurement. Bell says you may keep one but not both, at least not in their classical forms. Now you might ask, okay, but maybe the particles coordinate at the source, they share a random plan. Good instinct. That's exactly what a hidden variable model would do. The source hands them matching instruction tables, like giving two students the same cheat sheet, but the inequality already accounts for that. It allows any shared randomness you want, infinitely complicated. The only rule is, once they separate, your choice of setting doesn't reach across and change my local response function. And yet, even with shared randomness, you can't exceed 2. Nature exceeds 2, so the cheat sheet idea fails. And you might ask, maybe the setting choices aren't really free. Maybe the universe conspires so that our random number generators are secretly correlated with the particles. That's a logically possible escape hatch. It's called superdeterminism. But notice the price. You're saying the very act of doing an experiment, choosing settings independently, is an illusion. The scientific method itself becomes suspicious because any test could be prearranged by hidden correlations dating back to the Big Bang. You can adopt it, but it's not a small patch. It's a new worldview. Or you might say, maybe there's faster-than-light influence, but it's hidden, so it can't be used to signal. That's another option. Some interpretations go that way, but then you're explicitly giving up strict locality, even if you keep no signaling. Or you might say, no, the outcomes just aren't there until measurement. The particle doesn't have a definite answer for a tiny answer ever you chose a tiny answer ever you grow. That's the option that keeps locality in a practical sense but abandons realism. And that's the fork in the road we can't avoid anymore. Because Bell's inequality isn't telling you what to believe, it's telling you what you are not allowed to believe simultaneously. In the next part, we'll do the existential accounting. If the universe isn't locally real, what kind of reality is left? What stays solid? What becomes relational? And why this doesn't mean anything goes, but the opposite, nature is stricter than your intuition ever asked it to be. So what kind of reality survives after Bell? Because it's not enough to say classical intuition fails. Classical intuition always fails somewhere. The question is what replaces it. Here's what doesn't change. When you do an experiment, you get a definite outcome. A detector clicks. A mark appears on a screen. A bit flips in memory. Physics still predicts those outcomes with ridiculous accuracy. The world is not becoming foggy. What changes is the story you're allowed to tell about what was there before the click. In a locally real universe, you picture the world like a mosaic, little tiles of reality spread out in space. Each tile has its own color already painted. When you look, you just find the color. Bell says the mosaic picture cannot be the whole truth. The correlations show that the color is not just a local paint job on each tile. The joint pattern behaves as if the tiles are not independent objects carrying independent facts. It behaves as if the most primitive thing is the relationship. That sounds philosophical until you realize it's exactly what the math and experiments are screaming. And there's a subtlety here that matters. People hear non-local and imagine a secret signal traveling faster than light, like a cosmic telegraph wire. But that's not what the data demands. The data demands asterisk, asterisk, non-separability, asterisk, asterisk. The idea that the state of the whole system is not reducible to a list of states of its parts. Think of a single sheet of paper with one sentence on it. You tear the paper into two halves and send one half to me and one to you. Each half alone might look meaningless, half words, broken letters. But together the halves aren't independent. The information lives in the way they match. That's closer. But even that analogy breaks, because with paper the sentence is still written before the tearing. In quantum mechanics, the sentence isn't a pre-written message you're merely reconstructing. It's more like a rule that only becomes concrete when you choose what question you're asking. So we end up with a reality that is real because experiments have outcomes, but not realist in the classical sense of all properties exist in advance. Now, does that mean the moon isn't there when you're not looking? No. Don't be silly. The moon is entangled with sunlight, dust, cosmic rays, the rest of the universe. It's constantly being measured by its environment. Macroscopic objects have stable, redundant records everywhere. That's why the classical world appears classical. Bell is not telling you that reality disappears when you blink. It's telling you something more specific. If you try to model the underlying layer of nature as a set of local, pre-existing values that would have answered any measurement you might have chosen, then you will predict a Bell bound of 2, and nature will laugh and give you 2.8. So where do different interpretations land? Some people keep realism and give up locality in a controlled way. Bohmian mechanics is the clean example. Particles have definite positions, but they're guided by a wave function that is inherently non-local. It's deterministic, it's realist, but it admits that what happens here depends on a global object not confined to local space. Some people keep locality in the sense of no faster than light signals and give up classical realism. Copenhagen-style views say the quantum state is not a list of properties. It's a tool for predicting probabilities of outcomes given an experimental arrangement. The outcome is created in a precise operational sense at measurement. Many worlds keeps locality in the equations but changes what you mean by an outcome. All outcomes happen in different branches, and the correlations are explained by the structure of the global wave function. You don't get a single definite pre-existing value per run in the usual sense because the single run splits. Relational approaches say properties are not absolute, they are always relative to an interaction. The electron doesn't have spin-up as a global fact floating in space. It has spin-up relative to this measurement context. And notice something, all these views disagree violently about what reality is, but they agree on the constraint Bell forces. Whatever reality is, it's not a locally pre-labeled set of facts. There's also a limit here that's beautiful. Quantum mechanics violates Bell inequalities, but not arbitrarily. It doesn't blow past every conceivable bound. It hits the Tserilson bound 2√2, not 4. Nature is weird, but not chaotic. It's as if the universe says, I won't let you keep your classical picture, but I also won't let you have unlimited non-local correlation either. That should bother you in the right way. It means this isn't a loophole, it's a structured feature. Now zoom out. Why does this matter for anything beyond physics gossip? Because local realism is basically your default belief about being a self in a world. You feel like a little object inside your skull. Separate with your own properties, your own private state. And the rest of the world is out there, separate with its own properties. Information travels between you and it, and that's how you learn. That picture works brilliantly at human scale. It's the reason you can catch a ball. But underneath, the universe does not seem to be built out of little independent parcels of truth. It seems to be built out of constraints on relationships, correlations that cannot be reduced to local storybooks. So maybe the deep lesson isn't reality is subjective or nothing is real. That's cheap. The deeper lesson is the most fundamental description may not be things with properties, but interactions with consistent outcomes, stitched together by rules that are global, in a way your instincts never evolved to handle. And there's a strange comfort in that, because if reality were just a pile of local facts, the universe would be like a warehouse inventory. Item A has label X, item B has label Y, end of story. But the actual universe behaves more like a piece of music. You don't understand a chord by inspecting a single note in isolation. The meaning is in the combination. The harmony is not located in one string of the guitar, it lives in the relation. Again, not poetry. A statement about what kind of explanation survives contact with Bell tests. Now one more practical point, because this always comes up. Does this break causality? No. The no-signaling structure of quantum mechanics is incredibly strict. You can have correlations that defeat local realism and still have a world where information cannot be transmitted faster than light. That's why relativity survives. That's why you don't get paradoxes for free. So the universe is not saying everything can influence everything instantly. It's saying your classical way of carving the world into independent, locally real chunks is not how the correlations are organized. If you want a final image to carry with you, keep the envelopes, but fix the mistake. Don't imagine the envelopes contain two separate pre-written numbers. Imagine they contain a rule that only becomes a number when you choose a question, and the two answers are linked by a pattern that cannot be explained by pre-written local lists. The thing is not the individual number, The thing is the constraint tying the numbers together across all possible questions. That's what Bell cornered, that's what experiments confirmed, and once you really swallow it, you can't go back to the old story without lying to yourself. If you like this kind of physics, the kind that doesn't just give you equations but forces you to renegotiate what you mean by real, then stay with this channel. We'll keep doing it the honest way. No mysticism, no fake certainty, just the sharp edge where experiments cut into intuition. Next, we can take this one step further and ask the brutal follow-up. If local realism fails, what exactly is a quantum state? Is it a physical object, a bookkeeping device, or something in between? Because the answer to that question decides what kind of universe you think you live in.